Okay, hello. So we're going to start with a brief review of complex numbers. I expect that you should have seen all of this before, but it's worthwhile going over this quickly. So a complex number can be described as z equals x plus jy, where j is what we are calling the square root of -1. So you've probably seen this before, but using the variable I. So we don't use I in this class or in electrical engineering in general because I is reserved for current, which we haven't talked about yet, but we'll use it later. So when you express the complex number in this form, this is called rectangular form. And can be quickly plotted on the Cartesian coordinate system, the x and the y axes. So, well, I'll tell you what. So what we'll do is denote the value x located here and the value of y located here, such that z is really a vector on this Cartesian plane describing this complex number. Okay, so we see that if we look at the real portion of z, we get the value x, and if we look at the imaginary portion of the complex quantity z, we get the value of y, which would denote this point on the Cartesian plane. So we can also call the x-axis on this Cartesian coordinate system the real axis, and the y-axis as the imaginary axis. So once we plot it this way, we've got a nice convenient new form that we could describe the complex quantity of z as well. Noting that this vector on the real and imaginary plane has a length r and an angle off of the real axis of theta. So we can describe z now in a new form where z is going to be the radius of this vector, or the length of the vector, r, at an angle theta. And so this is what we call the polar form of the complex number z. Of course, you can relate the two quantities together, so let's review here. We've got z can be described in rectangular coordinates as x plus jy, and as polar coordinates as r angle theta. So we can now relate the two together, again, just by simply looking at the triangle formed by that complex number. So we note that the height of this triangle is y, and the base of this triangle is x, and the hypotenuse is r. So using some basic geometry, we can find that r is the magnitude of the triangle, or the square root of x squared plus y squared. And the angle theta is going to be given as the arctangent of y over x. Likewise, you could flip how we relate the two, and we can find x based on the polar version of the coordinates as being the hypotenuse times the cosine of the angle, y as being r times the sine of the angle. Okay, then we can rewrite z from the rectangular coordinate system by subbing in the values of x and y based on the polar form. And we can see that z also then equals r cosine theta plus j r sine theta. This is interesting because this gives us a new form of the expression, and this equation is what we call Euler's identity. Note that this is pronounced Euler, spelled E-U-L-E-R. And the identity is that when we have a real cosine plus an imaginary sine, that's the same thing as, we're going to pull out this r first of all. The same thing as a complex exponential raised to the angle theta. So e to the j times theta. You could prove this out if you wanted to using Taylor expansions. But to summarize, we've got three forms of the complex number now. Z equals x plus jy, is rectangular coordinate system. Z is r angle theta for the polar form of the coordinate system. And we can also express it as r times e to the j theta. And this is what we call the exponential form of the expression, or sometimes the complex exponential form. Okay, so you should be able to relate these forms back and forth between one another. So if you were given a quantity in rectangular form, you should be able to find the polar expression of that, as well as the complex exponential. Note that there's really no difference in finding the polar and the exponential form, because in both cases you're finding r and theta. Just need to understand how to write them a little bit differently. The reason we do this is because in circuit analysis, this exponential form of the complex number is going to be a really important quantity, or a way of describing a signal. And that really boils down to the fact that calculus is relatively easy when we're dealing with exponentials. As a reminder, the integral and derivative of an exponential just is the exponential back itself. So it turns out to be a really cool little mathematical trick to use this form of the expression. Okay, so a couple cautionary notes in finding the polar coordinates of a complex number. So let's just, and this has to do with the quadrant of the Cartesian plane that we're dealing with when finding the complex number. So let's consider the real and the imaginary plane. We can denote these quadrants as quadrant 1, 2, 3, and 4 going around counterclockwise, starting in the upper right. So you can see that we can describe a complex number in any of these. So we'll call that Z1, Z2, Z3, and so forth. Okay. So in all cases, when we are trying to determine the value of r and theta, in this case r1 and theta1, note that when we pull this triangle out, we're always assuming x and y as being positive quantities. So we know that the value of theta when using the expression arctangent of y over x is always going to be positive and always going to be less than or equal to 90 degrees. But it's important to denote what theta is relative to the positive real axis. So if we do the same thing for quadrant 2, we're not actually finding theta anymore. I'll call it phi over here when looking for R2, and phi. So phi 2 using this expression is just going to give us arctangent of y2 over x2, again going to be between 0 degrees and 90 degrees. Problem is that what we found is not the right angle. We want to find theta, which is always denoted as the angle from the real plane. Okay, so in order to find theta 2, we take phi 2, we have to take the negative of that and add 180 degrees to the solution. Okay. In other words, we can write find theta 2 directly by saying 180 minus the arctangent of y over x. Okay. So you do this so that you know, let's get rid of this, so that you can ensure that the solution to theta is going to be less than 180 degrees, but also greater than 90 degrees. You know that it has to be in that bound. Okay. Likewise, for theta 3, we know that it's going to have to be somewhere between 180 and 270 degrees. And then finally, for theta 4, it's going to be something less than 360, but greater than 270. Of course, 360 also being 0 degrees again. So it's always important to note what quadrant your complex number is going to be in before going to compute your angle, because this is a very common mistake I often see is everybody will quote me the smallest angle, which may not be the correct angle. Okay, so it's just important to note if you've got something in quadrant 1, meaning x is going to be positive and y is going to be positive, you know the angle is going to be between 0 and 90 degrees. If you're in quadrant 2, you know that x is negative, the real part is negative, and the imaginary part is positive. That's going to be between 90 and 180 degrees. Quadrant 3, both the real and the imaginary portions are negative. That's going to denote 180 degrees to 270 degrees phase. And then quadrant 4, the real part is positive, but the imaginary part is negative, and that's going to put you with angles in that domain.